It turns out you can describe fluid flow in two frames of reference, the Lagrangian frame of reference or an Eulerian frame of reference. And the governing equations for fluid flow are usually written in the Eulerian frame of reference, so we need to understand what that means. One of the few things I remember from high school physics is applying F equal to ma to a ball being thrown, and one can integrate the equation and get the parabolic trajectory for the ball. By the way, this is a prop that my daughter kindly lent me. And in that case, we are using the what would we call a Lagrangian frame of reference because we are following the ball. Though I didn't know that at that time in high school. Here, instead of having a ball, what we have is an infinitesimal fluid particle. In fact, we have an infinite number of infinitesimal fluid particles, and it becomes impossible to follow an infinite number of particles. Instead, what we do is we follow points in space. And when we do that, we are switching over to an Eulerian frame of reference. Let me unpack that a little bit more. If I go back to the infinitesimal fluid particle moving within the channel, let's say at some time t0, particle p, so I would say this is particle p, and this is the time t0. At that time, the particle is at x0, y0. So this location is x0, y0. This is a two-dimensional view. One can extend this to 3 dimensions quite readily. So this is my coordinate system, and I have the location. Then I would say that the velocity of the particle at time t0 is some value v0. And its position in the x, the x position at time t0 is x0, and its y position at time t0 is y0. So here I'm following what's happening to the particle, and this would be called a Lagrangian view or a Lagrangian description. The problem with this view, which works very well for a ball being thrown, but not here, is because we have an infinite number of infinitesimal fluid particles. So what we do is instead we switch to following points in space. So we will say the velocity at x0, y0 at time t0 is equal to v0. So there's a shift in view here where instead of following the particle, we are following points in space. And the way to interpret this is, the particle, when it moves through location x0, y0 at time t0, it's going to have this velocity. That's what you need to think in your mind. Because the assigning that velocity to the point is an abstraction, because the point itself doesn't have a velocity. So this would be the Eulerian view. And let's say, I keep staring at this point, and there are a bunch of particles coming through, and every particle has the same velocity v0, irrespective of what the time is. So we'll say, hey, in this particular case, there is no dependence on time, and I'll just say that the velocity at location x0, y0 is just v0. And this would be the case of steady flow. So the velocity of the particle changes, but every time any particle comes to that particular location, it will have the same velocity. That's what steady flow means. And which means that in the Eulerian view, we're reduced to knowing the velocity everywhere within our flow domain. So once we know velocity as a function of x and y, then we can know what any particle if we know a particle is at a particular location, we just need to look up what that the velocity at that location is, and we know what the velocity of the particle is. So this is called a velocity field. And this is called a velocity field, and this would be a two-dimensional velocity field. We can also extend this idea to having a variation in the z direction. This is a function, and in 2D, so you'll have two components of velocity. You'll have the x component, which is usually written as uxy. We'll have the y component, which is also going to be a function of x and y. And then we need to know the pressure. So this would be 2D, and we're also assuming that there is no change in density, which is incompressible, which means density is not a function. So in 2D incompressible flow, with the steady assumption, we need to determine three fields or three functions, each of which is a function, it's a two-dimensional function, it's a function of x and y. So when looking at the governing equations of fluid flow, whether in differential form or integral form, we'll be using the Eulerian viewpoint.